Next, we will continue our look at reactions of aldehydes and ketones by focusing on nucleophilic addition reactions. Unlike the ones we saw before that were irreversible, this new set of nucleophilic addition reactions are reversible. So we will be looking at a variety of nucleophilic addition reactions. In our first example, water is added to convert an aldehyde to a hydrate. Next, an aldehyde is treated with hydrocyanic acid to form a cyanohydrin. Next, an aldehyde can be treated with alcohol to form first a hemiacetal, but then with additional alcohol, it will form what's called an acetal. An aldehyde can be treated with a primary amine to give a carbonylamine, also called a hemiaminal, but then this typically loses water to form an imine. And then finally, an aldehyde can be treated with a secondary amine to form, again, a carbonylamine or hemiaminal, but this will lose water to form what's called an enamine. So we're going to talk about all of these reactions with both aldehydes and ketones. We are first going to focus on reaction with water to form a hydrate. And we will also develop the mechanistic information about the nucleophilic addition reaction overall. And then in separate videos, we will look at the formation of cyanohydrins, acetals, imines, and enamines. So our first type of nucleophilic addition reaction is reaction with water to form a hydrate. So we could think about the reaction like this, where water acts as the nucleophile and it adds here to this carbonyl carbon, pushing these electrons up onto the oxygen. That would give us this intermediate with an O- and an O+. And then we would have to think about proton transfer reactions, and then finally leading us to the hydrate. So this is overall the change that we're looking at, but this isn't a real reaction because typically these reactions are done either under basic conditions or under acidic conditions. Because as it is, this is not a very good nucleophile and this is not a good enough electrophile, so typically no reaction will happen. But if the reaction is carried out under basic conditions, well, that means we're using hydroxide. Hydroxide is a much better base and so also a much better nucleophile. So this can share its electrons here, push these electrons up onto the oxygen, and that will give us, this is OH from the hydroxide that was just added, and this is still the H. And now this can react with another molecule of water. The O- can grab off a proton, and that gives us this. Alternatively, the reaction can be done under acidic conditions. So under acidic conditions, the carbonyl oxygen can act as a base and grab a proton. And so that will give us the protonated carbonyl, so that when it's treated with water, this is still not a very good nucleophile, but our electrophile is now much more electrophilic. So water can add here, push these electrons onto the oxygen, and that gives this intermediate. And then finally, water can act as a base, grab off a proton, put these electrons back onto the oxygen, and that gives us the hydrate as the final product. So up here we had a weak nucleophile and just an okay electrophile. Here we still have that same okay electrophile, but now we're using a much stronger nucleophile, and so this reaction will proceed. Here we still have the same OK nucleophile, but our electrophile is now a very good electrophile because it's protonated, and so that allows the reaction to proceed as well. Notice in both reactions we are looking at going from an sp2 hybridized carbon to an sp3 hybridized carbon. Here we have nucleophilic addition followed by proton transfer. Here we have proton transfer followed by nucleophilic addition followed by another proton transfer. In both cases, proton transfer to and from oxygen is going to be fast, and so the rate determining step will be nucleophilic addition. So under basic conditions, it is the first step, and under acidic conditions, it is the second step that will be rate determining. Now we're going to focus on hydration under basic conditions, and the rules that we develop are going to be the same thing as under acidic conditions, and they're also going to apply for other nucleophilic addition reactions. So the formation of the cyanohydrins and the hemiacetals, all of that will follow the same information here. So here we have the reaction under basic conditions, and again the hydroxide acts as the nucleophile, pushes these electrons up here, giving us this intermediate, and then this will grab off the proton, pushing these electrons back onto the oxygen, giving us our final product. So if we look at this on an energy diagram, well, this is going to look something like this, because this is an intermediate and this is the transition state leading to that intermediate, and then from here it is going to go here. This is another transition state, and this is our final product. So this reaction is made up of two elementary steps. The first step, we have this starting material to transition state to the product of the first step. And then the second elementary step, we are going from the starting material to the transition state to the product of the second step. Now, for these reactions, we are going to consider the rate of the reaction. Now, for the rate of the reaction, we need to focus on the rate determining step, which is nucleophilic attack. And we need to remember that the activation energy determines the rate. So what we want to focus on is the energy difference between the starting material and the transition state. But because we can't always get information on our transition state, it is helpful to get information on the intermediate, because we know that the transition state will be similar in energy to the intermediate. So for the rate of the reaction, we want to focus on the starting material going to the intermediate. We are also going to consider the position of equilibrium. So now we're thinking about the delta H, which gives us information on the position of equilibrium. And so here we need to think about the relative stability of the starting material compared to the product of the whole reaction. All right, so we'll be looking at this compared to this for information on the equilibrium. So starting material to the final product. So as we think about the equilibrium, remember that the equilibrium can be described by an equilibrium constant with a capital K, and this is equal to the concentration of products over the concentration of reactants. And more specifically, what we're talking about here is the concentration of the hydrate over the concentration of the aldehyde or the ketone. So looking at a few different compounds, if we are thinking about formaldehyde compared to acetaldehyde compared to acetone, then if acetaldehyde has a relative equilibrium constant of 1, then for formaldehyde, this has an equilibrium constant that is 2,300 times higher. In other words, K is much bigger, and so there is a lot more of the products than there are of the reactants. And so in this first case, we're looking at about 99.9% hydrate and only 0.1% will exist as formaldehyde itself. Looking in the other direction at acetone, now this equilibrium constant is smaller than the equilibrium constant for acetaldehyde itself. So in this case, what we're looking at is about 0.14% of the molecules will exist as the hydrate, and the rest are going to exist as acetone itself. Now, we should also think about the rate of the reaction, and the rate is equal to a rate constant K times the concentration of the carbonyl containing compound, so our aldehyde or ketone, times the concentration of hydroxide. And if we look at the same examples and we call acetaldehyde, let's say that has a rate constant of 1. The rate constant for formaldehyde is 2200 times larger. And so that means it is a much, much faster reaction. And for acetone, the rate constant is a lot smaller, which means it's a much, much, much slower reaction. As we are considering ketones compared to aldehydes, compared to even simpler aldehydes, we see a significant difference both in terms of the equilibrium and in terms of the rate constant. Now, what we want to do then is figure out how does the structure affect the rate of the reaction and how does it affect the position of equilibrium. And so in both cases, we're going to be considering both electronic factors and steric factors, but we will be looking at different species, because remember, for equilibrium we care about the reactant and the product, whereas for the rate we care about the reactant and the transition state of the rate determining step. So as we consider the effect of structure on the position of equilibrium, we want to consider number 1, sterics. So if we think about our starting material, here we have our groups at 120 degrees. So having a hydrogen versus an alkyl group, either way, we've got plenty of space. So sterics for the starting material aren't going to play a big impact. But when we look at the product, now this carbon is sp3 hybridized, and so we're looking at bond angles of 109.5 approximately. And so here the size of the R group is going to play a bigger role. So as we consider the role of sterics, we're going to focus on the product. And here we have a hydrogen, and these are both pretty small, so they're not going to be bumping into those OH groups very badly. If we look at acetaldehyde, well, we still have the small hydrogen. Here we have a bigger methyl group, so this is going to start to get in the way of the hydroxyl groups. And now with our ketone, now we have 2 alkyl groups which can both be bumping into the OH groups. And so this is going to be the most crowded, and so this is going to be the least stable. So by steric effects, the aldehydes are going to be more stable, and then the ketones are going to be less stable. Another feature we need to think about would be electronic effects. So as we're thinking about electronics, we're thinking about how the oxygen is pulling away electron density from the carbon, and then the carbon tries to pull electron density from whatever it is next to. The inductive effect is going to be kind of similar between our starting material and our product. But in the case of our starting material, we can also draw another resonance structure that looks like this. So we also have resonance effect playing a big role. So in our starting material, we've got a big partial plus and a big partial minus. So it's going to be especially important for this carbon to be able to get some electron density from what it's connected to. So for electronics, we're going to focus on the starting material. In the first case, we have this carbon with a big partial plus trying to pull away electron density from the hydrogens. But the hydrogens can't release a lot of electron density. So that means they can't help stabilize the positive charge. Looking at the other extreme where we have acetone, now we have two alkyl groups that can both release some electron density. They can take on a partial positive charge, and that is going to help stabilize the partial plus that is on this carbon. And so because the alkyl groups can share electron density, that is going to make this the most stable. So when we try to pull together that information to think about the effective structure on the position of equilibrium, for the starting material, we want to focus on electronics, and we're thinking about stabilization of the partial plus on the carbon. So let's just put acetaldehyde right here. We know that acetone is going to be more stable because having two alkyl groups to release electron density, that's going to help stabilize the partial plus. And we know that formaldehyde is going to be higher in energy because those hydrogens cannot stabilize the positive charge, the partial positive charge, and so that will be higher in energy. And when we think about sterics, we are going to focus on our product. So again, we're just going to put acetaldehyde here. We're just normalizing this so that we're saying if acetaldehyde has an equilibrium constant of 1, then these would be at the exact same energy. That's not actually true. It's just that this is the way that we're using this for comparison. So now, as we think about sterics, because the hydrogens are much smaller than something with more hydrogens, such as the formaldehyde hydrate, this is going to be lower in energy, more stable, and something with more alkyl groups, in other words, the acetone hydrate, this is going to be higher in energy. So what does this give us? If we compare acetaldehyde, we set these up on the same level to give us a relative value of 1. When we look at acetone, we start out lower in energy, but we end up higher in energy, and so this equilibrium is not favorable. So that's why we have a very small equilibrium constant, and we know that at equilibrium, most of it is going to exist as the ketone, not as the hydrate. When we look at formaldehyde, we are starting out higher in energy, but we end up lower in energy, and so that means our equilibrium constant is much larger, and that means at equilibrium, most of the product is going to exist as the hydrate, not as formaldehyde. So by focusing on both electronics and on sterics, we were able to come up with an explanation for the relative position of equilibrium for these different compounds. Next, let's consider the effective structure on the rate of nucleophilic addition reactions. So once again, we want to think about electronics and sterics. So for electronics, we should again think about the starting material. It's the same situation that we're looking at, where if we compare acetaldehyde with formaldehyde, we know that formaldehyde will be higher in energy because those hydrogens cannot stabilize the partial plus, and we know that acetone will be lower in energy because the alkyl groups can help stabilize the partial plus. And if we look at sterics, well, remember, for rate of reaction, we are looking at the starting material compared to the product of step 1, which is the intermediate. We really want to have information on the transition state, but we are using information on the intermediate to give us information on the transition state. So when we think about sterics, if this is what we've got for acetaldehyde, then formaldehyde, we expect that to be lower in energy because this is more stable, less crowded, and higher energy is what we expect for the acetone intermediate. Remember, according to Hammond's postulate, then we can use this information about the intermediate to estimate information about the transition state. So if this is the transition state for acetaldehyde, then maybe a little bit lower in energy would be the transition state for formaldehyde. And then a little bit higher in energy, this would be the transition state for acetone. So now when we look at the rate of the reaction for formaldehyde, this is the activation energy. For acetaldehyde, this is the activation energy. And for acetone, this is the activation energy. And that is exactly what we see here. For formaldehyde, this has the smallest activation energy, which gives us the fastest rate of the reaction, and so the largest value for K. Acetaldehyde is in the middle, medium size activation energy, and so that's why we have a rate constant of 1. And then acetone, it is lowest energy to begin with, but highest energy transition state because it's highest energy intermediate. So this gives us the largest activation energy, which gives us the slowest rate of reaction. So to summarize then, in terms of equilibrium, for an aldehyde, the equilibrium typically lies to the right. For a ketone, the equilibrium lies to the left. And as we think about the rate of reaction, the reaction of aldehydes will be much faster than the rate of a ketone. So let's try to apply that to a couple of other examples. So let's say we are looking at benzaldehyde compared to acetophenone, and we want to know which one has the larger rate constant K. Well, what we're looking at is an aldehyde compared to a ketone. So we know that aldehydes are faster than ketones, so this one will have the larger rate constant K. What if we were looking at trifluoroacetaldehyde compared to acetaldehyde, and we want to know which one has the larger equilibrium constant K? Well, now we're talking about both aldehydes. So let's not just kind of memorize it this way, but let's think about what we derived in terms of relative stability of starting materials and relative stability of intermediates or products. So here we would be looking at, because we're looking at equilibrium constant, we care about our starting material compared to our product. So if this is the energy of acetaldehyde and this is the energy of the acetaldehyde hydrate, well, first of all, let's think about the electronics of the starting material. If we have if we're talking about a trifluoroacetaldehyde, then here we have a big partial plus, And the only way that this carbon is stabilized is by pulling away electron density from this carbon, but all of these fluorines are pulling away electron density as well. So this carbon isn't going to be able to help this carbon, and therefore we would expect that this would be higher in energy. So the CF3 is going to be higher in energy. If we think about sterics, then we want to compare the products, and having the 3 fluorines, so instead of having this carbon has 3 hydrogens, if instead it had fluorines, it's going to make it a little bit more crowded, but fluorines are not really that big, and so while it probably will be more crowded and so less stable, it's probably going to have only a small impact on the energy. So what we see then is that if this is the relative energies of our starting material versus our product for acetaldehyde, then this would be the relative energies of our starting material versus the product for the trifluoroacetaldehyde, and therefore we would expect this one to have the larger equilibrium constant. So this difference in reactivity between aldehydes and ketones, both in terms of equilibrium and rate of reaction, this is something that's going to become important throughout the rest of the semester as we look at a number of different types of reactions. But rather than just memorizing this fact, it's important to think about this analysis, right, of being able to compare the relative energies of starting materials, the relative energies of products, if necessary, the relative energies of intermediates, to be able to deduce relative reaction rates or relative positions of equilibrium. Now that we've gone through this information for the formation of a hydrate, all of this is going to apply to the other reactions that we're looking at next. So whether we are talking about the formation of a hydrate, the formation of a cyanohydrin, the formation of an acetal, in all of those cases, equilibrium is more favorable for the aldehyde product and more favorable for the ketone as the ketone. The rate of the reaction will be faster for aldehydes being converted to those nucleophilic addition products than it is for ketones.